Are your rockets shape-stupid and spinning out of control? Are you incapable of designing a rocket with balanced thrust? Are you sick of constantly smashing F9 to forget your failures? Why not try quadratic programming? Quadratic programming can fix your poorly designed vehicles and make you look more competent than you really are. Wow, look at those monstrosities go.
Just write down the problem, rearrange until you have a quadratic equation, throw that at a quadratic program solver.
Bam! All your problems are solved. Warning. Quadratic programming has known side effects including but not limited to extended 1,000-yard stares, chronic crying, sporadic screaming, and nightmares of non-positive semi-definite matrices. Ask your professor about quadratic programming today and start living! As the title suggests, we'll be talking about quadratic programming in a particular way that I've found to apply it in Kerbal Space Program. Before that, we'll talk about the problem we're trying to solve. Quick side note, the details in the rest of the video are mostly in the language of linear algebra, so if you aren't familiar with that, I'd highly recommend 3 Blue 1 Brown's Essence of Linear Algebra, link in the description. And with that, let's get into it. When building rockets in Kerbal Space Program, you may not have run into issues with torque balancing. This is because the engines usually just go on the bottom of the craft, or are at least placed using the symmetry tool. KSP shows the center of mass with the black and yellow ball, and shows the center of thrust with the pink arrow. When building with the symmetry tool, the engine's torques cancel each other out, and the center of thrust is aligned with the center of mass. However, when building vessels in this way, the results can be very tubey, tall, and prone to tipping over. If you venture off the symmetric path and try building things that are, more interesting, you might find that the craft tends to spin out of control. This is caused by the center of thrust not being aligned with the center of mass. Quite often, changing the thrust limits for the engines can bring the center of thrust to be aligned with the center of mass again. If the thrust points through the center of mass, then no torque is generated and the vehicle will fly stably. Problem solved, right? Not quite. As the fuel drains, it can shift the center of mass, causing misalignment again. That would mean we would need to realign the markers frequently while in flight as the fuel drained. Instead, I decided to write a script using KRPC to keep these aligned for me. I did this by framing the problem as a quadratic program. So, what is a quadratic program? Mathematicians use the word program to mean a minimization problem. Although I did use a Python program to solve our quadratic program, but that's beside the point. Anyway, a quadratic program is just a minimization problem where the function we're trying to minimize is a quadratic. Usually, quadratic programs are written in a form like this, where this is the function we want to minimize, this is a set of inequality constraints, and this is a set of equality constraints. These constraint equations let us put bounds on where we look for solutions. For our purposes in this video, we won't need the equality constraints. If you haven't seen a quadratic expression in this format before, I highly encourage you to go through the matrix multiplication to convince yourself that this is indeed a quadratic. Also, instead of using the variable x, we'll use alpha. Instead of writing my own quadratic program solver, I used an off-the-shelf solution. In general, to get one of these solvers to solve a given problem, you must first write it down in this format and package that up into code. With that in mind, we can now tackle writing down the torque balancing as a quadratic program. To write down torque balancing as a minimization problem, we need something to minimize. In this case, we can minimize the magnitude of the torque imparted to the vehicle. Minimizing the square of a vector's magnitude also minimizes the vector's magnitude, which is what we will actually do because it makes the expression a nice quadratic in the end. Let's work up to that from the basics. As mentioned earlier, a torque is generated when a force is applied at an offset from the center of mass. This is usually represented in the equation torque is equal to force cross position, where position is the vector pointing from where the force is being applied to the center of mass. Since we have multiple sources of torque, we will attach to each of these variables a subscript to keep track of which engine it came from. However, we are interested in how much torque the engines produce when they have some throttle limit imposed, which we represent with a tilde over the torque symbol. we use the variable alpha to represent the throttle limit, which is how much of the engine's thrust it will produce. An alpha of 0 means no thrust at all, and an alpha of 1 being the maximum thrust available to that engine. Since each engine has its own throttle limit, alpha will also have a subscript. The cross product has a nice property where if you scale one of the input vectors, it has the same effect as scaling the output vector. So, we can scale the torque by alpha to get the torque generated when the thrust limit is imposed. By adding the contribution of each engine, we get the total torque on the vehicle. Remember, we want to minimize the squared magnitude of this torque vector, which is the dot product of the vector with itself. If we do some algebraic manipulations to this expression, we see that we get an expression that is a quadratic, since the highest power of any of the alphas is 2. Finally, we rewrite the expression in vector form. Here, P is a matrix where the value at row I in column J can be computed using the expression on the right. With that, we now have the function that we want to minimize written as a quadratic. Next, we need to rewrite the constraints on the thrust limits into the standard quadratic programming format. We start with our inequality for a given alpha and rewrite it in vector form. This curly less than means that each corresponding element of the vectors obey the inequality. That is to say, each alpha is between 0 and 1. We break this into 2 separate inequalities. Then, we flip the left one to get the alpha on the correct side. But now the inequality doesn't use the less than or equal to format typically used in quadratic programming. To fix this, we multiply both sides by -1. This flips which direction the inequality faces. Now, we recognize that alpha is the same as the identity times alpha. In doing so, we found the matrix G and the vector H. We now have our problem written in the standard quadratic programming format. Let's go plug it into a quadratic program solver and see what happens. We code that up in Cassidy, we have krpc implement the solution, and no thrust. Let's have a look at the graph for the quadratic function we're trying to solve. So it looks like we have an infinite valley of 0 torque solutions. This valley corresponds to configurations with balanced torques, but differing amounts of thrust. The quadratic program solver is likely starting with all zeros as the initial guess at the solution, and that happens to be in line with the infinite valley, because no thrust results in no torque. So, how do we incentivize the solver to return solutions that are further down the valley, resulting in higher thrust values? Well, earlier, when I showed the standard form for quadratic programs, there was a linear term that our cost function doesn't have. We can use this linear term to reduce the cost of configurations with large thrust limits. Technically, finding the correct value of this linear term is as hard as the original problem. Links in the description for more on that. However, a reasonable first guess, which is technically incorrect, but it's close enough for Kerbal, is to use the negative of the maximum torques that the engines could produce. This way, the solver is incentivized to produce as much torque, and therefore thrust, as it can from each engine, while not being too unbalanced. Alright, let's add that term into the code. Now the solver balances the torques and produces thrust. This works on a wide variety of vehicles, allowing for many unique designs that would have been incredibly challenging to fly before, including vehicles with constantly moving engines. Or ships composed of several components docked in orbit. If you enjoyed the video, please press the like button. If something wasn't clear, ask in the comments. I'll do my best to clarify. Subscribe for more sporadically occurring nerd content, but that's it for this one.